So again, one more time, let's say this out loud again. Atoms very, very, very rarely hang out by themselves. So they create bonds, which is the entire reason we have life itself. Okay. Again, second bullet is a test question. I need you to know what a chemical bond is. What is a chemical bond? Is a mutual. What does mutual mean? Okay. So they both agree. Okay. They're both okay with it. It's not forced. Now, sometimes we can get to the point where it gets forced, and I'm going to talk about that, but most of the time it's mutual. Electrical attraction. Let's stop there. What does electrical attraction mean? Positives and negatives. Okay? Positives and negatives. Where does the positive come from in an atom? Protons, which are found in the nucleus. Where do electrons, where does the negative come from? And where do they come from? And don't say cloud. Orbitals. Very good. Orbitals. Let's keep going. Chemical bond is a mutual electrical attraction between the nuclei, and then highlight this word. Valence. That is important. The valence electrons of different atoms that binds them together. The reason it's important is first and foremost, what does valence mean? It's the outermost. So whenever atoms bond, they are using the ones that are farthest from the nucleus. Okay, we're not talking about the core electrons. We're not talking about the ones closest. It's the ones on the outside. Okay. Now, bullet 3 is also a test question. I'm going to read it. I'm going to give you in science terms, and then I'm going to give you kind of a real-world relationship. I try to do that. I try to give it to you in science, real world, and then bridge the gap. So here's the science. By bonding with each other, atoms, know this, decrease their potential energy to become more stable. That's the science. When they bond, they decrease their potential energy. How do you think I contribute on a test question with that part? Increase. I could say increase, right? It's not increase. When they bond, they decrease their potential energy to become more stable or unstable. More stable. That's the test question, right? You got to know the two relationships. When they bond, it's a decrease for more stability. Now let me give you a real life example. When you were a kid or you have a sibling, did you ever get lost in a store? I vividly remember I was about probably 4 years old or less when this happened. Y'all may not even know this because this has been torn down since before you were born. Do you know where the Home Depot is? Yes. You know, there was a Walmart there before that. Yeah. Okay, so I was probably before. I got lost in that Walmart. Didn't know where my mom was, freaked out, panicked. I had to call the overrated comforter to come get me. Happens, right? Kids. So my point is this: is when I got farther from her, right? I lost my bond. I was freaking out. I was panicking. I had high energy. So if you're bonded, are you bonded with your mother? The closer you are with her as a kid, right, the more happy you are, the more calm you are, the more stable you are. So when you're closer to each other, when you're bonded with each other, the less energy you have to expend worrying, the more stable you become. Does that kind of make a logical connection, right? It's just an easy way for you to remember that. When you're with your mom as a kid, you're happy, you're safe, you're stable, you're not as energetic, okay? All right, so that's number 1. Now, these are the 4 types of bonds we're going to talk about. I need you to put a star beside the first one and the 4th one. Those are the 2 we're going to mainly focus on, but I'm at least going to introduce you to the other 2 types. So first and foremost, electrostatic attraction between ions. Let's talk about that word. What is an ion?
Negatively charged.
Not just negatively. It's a charged atom. Okay? Now, you've got some space. I'm going to hop off of this and I'm going to go to my whiteboard, but I want you to also add this to it. There are 2 types of charged ions. Does anyone know? Insert, we do page, after current. There's 2 types. Okay, there's a positive one. Does anyone know what the positive ion is called? It starts with a C. We talked about it before. A cation. We talked about this before. There's an easy way to remember.
I just said something right.
Look in the middle. What's in the middle?
Positive.
A positive sign. It's an easy way to remember that, right? T looks like a plus.
You said write this down, right?
Yes. Now, let me show you where to write this. Write it out beside up here. Where it says charged atom, I want you to write number 1, sorry, and then number 2. And again, I don't have space, so I have to go to my whiteboard. The second one, what's the opposite of positive?
Negative.
Negative. Does anyone remember what the negative ion is called? Very good. Who said it? Anion. Well done. Now, there's an easy way to remember this one. Again, how do you remember the positive one? There's a T in the middle. It's a plus sign, cation. The way to remember this one is it's basically it's an acronym. It's a negative ion. Anion. A negative ion is an anion. It's a little bit of an acronym. Everybody okay with this? All right, so that's the first 2. Number 2, metallic bonds. Metal atoms bonded to several other what? That's metallic, right? Forms a network. There's 2 words I want you to write now. One of them is called pure. Can someone give me an example of a pure metallic bond? Some of you may be wearing it right now.
Iron.
What kind of jewelry?
Stainless steel. Iron. Steel.
What kind of gold?
14 karat gold.
How much wearing 14 karat gold?
24 karat. Now, no, this is important because I'm glad you said that. 24 karat gold is more valuable, right? It's higher cost, it's higher price. Why? It's pure gold. That's exactly right. It's pure gold. Now, gold by ounce is very, very expensive. Somebody asked me this in third block, and I'm going to be honest, I've never done the research. If I've heard it, I've just forgotten. I'm not quite sure why they use carat as a designation. It has to do with the weight of it and how it's massed out, but I don't know what a carat means. So please forgive me of what that means, but I just know this. So yes, 24 karat is a pure gold, but a lot of jewelry is not 24 karat, it's 14 karat. Why? Very good. Now, this sounds crazy, but gold, in terms of metal, is actually really soft. So if you're wearing jewelry, do you want it something to be brittle where it can break? No, you don't. So that is why they supplement the 14 karat with silver and a few other metals to make it a little bit stronger. So that makes it cheaper because it's not pure gold. Okay? Now, the other word here, it's either pure or. Does anyone know the scientific name for a mixture of metals? Say it again. Very good. It's an alloy. You may have heard that word before. Okay? It's an alloy. Steel is an example of alloy. If you pulled out a penny, is it an alloy? Yes, because is it pure copper? It's not pure copper. Why is it not pure copper? It does have zinc in it, but why is it no longer pure copper? It's too expensive to make it, right? The cost of copper is way, way high. So, does anyone remember what year they started doing zinc? 1983. 83. Okay, 1983. So again, alloy is a mixture of metals. Now, network covalent solids, we're going to talk about it. It's like 2 slides real quick and fast. Covalent is very, very important. So the key here, the key words you need to highlight here is shared. Okay? Also, I want you to write 2 words out beside it. Have you noticed there seems to be a theme of 2s? Ionic had cations and anions. Metallics had pure and alloys. Does anyone happen to possibly know the 2 types of covalent bonds? You've done this before. Polar? Polar, good. So, the 2 types of covalent bonds are polar or non-polar. I'm going to explain those more in details whenever we get to those at the end of this week. Okay? Now, second component to this. The only way we can break bonds. Now, what is a bond between? 2 or more atoms, right? It can be any of these 4. But to break those bonds, it must be a chemical reaction, right? Going all the way back to the very first unit. Remember we talked about there's 5 signs that you can see with your eyeballs that a chemical reaction has occurred. Raise your hand if you remember them. I want to call them out. Bubbles, write that down. Number 1 is bubbles. Underneath this slide. So the 5 signs of a chemical reaction. The first one is bubbles.
Heat.
Hey, I'm going to call it. Raise your hand. Let me call it. I'm going to go one at a time. And there's 2 parts. Heat and light. Heat and light. So it's kind of a hyphen, like a slash word. Heat and light. Color change is number 3. All right, so hang on. Slow down. Raise your hand whenever you're ready. Destiny, you write these down? Make sure you write them down, please. Okay. Bubbles, heat/light, color change was number 4. Rust. Very good. Hang on. The 5th one is the one that everyone always forgets.
Oxidation.
That is rust. Oxidation is rust.
No.
Those are all phase changes. Ready?
No. I'm not ready.
A solid precipitant.
Hey, I was gonna get that
A
eventually.
solid precipitant. Do you remember I kept showing you pictures and you take 2 liquids together and all of a sudden something kind of solid forms? Now again, is it like a rock? No, it's like coffee grounds. And how do you get that out of liquid? Filter. You pour it through the coffee filter, right? And it strains it out. So those are the 5 signs of a chemical reaction. So if we've got a covalent bond or an ionic bond or any of those other ones, to be able to break those bonds, a reaction must occur and these things must form. Okay? Or these things must be obvious and evident. So again, these are the 4 types of chemical bonds we're going to talk about. Today we're only going to focus on ionic. Now, this is a very important slide because it's got some content that you haven't been taught yet, and that's what that guided unit is about, but I'm going to give you some understanding to it. So, the degree. Okay? What I mean by the degree is to the amount. Okay? How much there is. The degree to which bonding between atoms of 2 elements is either ionic or covalent can be estimated by calculating the difference. What is difference in math? Write the word subtract above difference or around difference. Let me give you good news. We're not going to be doing any math in this class, but I'm going to show, in this unit, but I'm going to show you how simple it is. Okay? It's either ionic or covalent by estimating the differences in their electronegativities. It's like an 8-syllable word. Now, y'all know I'm a lazy teacher, right? You know I don't like writing big, ugly words like this, correct? So let me show you the acronym, and I want you to write this out beside it. This right here is the abbreviation for electronegativity. You will never, ever see me write that word out all by itself. So if you see me write ENEG, I am referring to electronegativity. Now, I got to be honest, I don't know where that came from, if I made that up, or if I saw it in a book somewhere. So that may just be a me thing. Okay? So if you hear me talk about ENEG or electronegativity, that's what it is. Now the second question has to be, what the heck is electronegativity? Do you agree that's a question you don't know the answer to? So, I would encourage you strongly to write this down. Now, in the unit that you're going to do in the self-guided, it's going to talk all about electronegativities. Okay? I'm going to explain the bullies and nerds theory. Underneath that slide we were just on, the one that said electronegativities. Lily, come up here. Come hold my bag of Doritos. Yeah, don't crush them, please. So hold them up so everyone can see. Thank you. Everybody knows Doritos, right? So if Lily is considered a super nerd and I'm considered a super bully, let's flip it. I'm going to hold these. I'm the super nerd. She's the super bully. You're hungry for a snack. And I'm standing there holding a bag of Doritos. What are you going to do?
Lillian,
Take my Doritos, right? Push me down, snatch them, do whatever you want.
do it.
She's already taken it.
down.
Now, let's say she's not quite as big and powerful. Now she's kind of a bully. I'm kind of not as much of a nerd. And she walked over to try to grab him. Try to grab him again. Now she's got him, right? Was there a little bit of resistance there, right? All right. So now we're on equal playing fields. Try to take him. Okay. She still got him, but at some point, thank you. Thank you, I appreciate that. Is there a point when it becomes where you can't get them anymore, right? Now what did the Doritos represent? Electrons. We represented the atoms. So the bullies and nerds idea is when you have some atoms that are more powerful, more stronger, okay? The key science word is more electronegative than the others. Now, what you probably need to ask yourself is, who are the bullies? Who are the nerds? Do I have any hypotheses of who you think the biggest bully on the periodic table is?
The one with less electrons.
Is it like fluorine? Fluorine.
It is fluorine. Very good. So I want you to write this down. Fluorine, you guessed, but there's some rhyme or reason behind it. There's a reason, and I'm going to explain it. Fluorine, you need to know that. Fluorine is the biggest bully, but that's the real world. What's the sign? Yeah, fluorine, letter F. Why? What is it really? It's not the biggest bully, it's the most what? E-neg. It's the most electronegative. Now, in terms of its location on the periodic table, top, bottom, left, right.
Right.
Top, right. It's the most electronegative. Fluorine is the biggest bully because it's the most electronegative. Since you're writing that, let me say that one more time. In terms of its location on the periodic table, where is it?
Top right.
Top right. Do me a favor. Everybody has a periodic table. Go ahead and pull it out and look at it because this is going to help, I think. If you don't have one, I'll pass one around. Anybody else not have one? Oh my gosh. Wow. Very good. Pass one more back all the way around. Do you need one? Come in. All right, so again, one more time, I know this is kind of, for the third time I'll say it. Where is it in terms of its location? Top right. All right, so let's just think for just a second. If fluorine is the biggest bully, most electronegative, top right, raise your hand, don't yell at me. Where do you think, location-wise, the biggest nerd is?
Bottom left.
Raise your hand, don't yell at me. Trinity. Bottom left. Trinity, who is bottom left? Francium, that's what I want you to write. So francium is the biggest nerd, but again, that's the kind of the humanistic side of it. What is its chemical trait? Try again. Least electronegative. Now, remember when I just read and Colin said, oh no, you can actually calculate these differences? There are values that have been assigned to each atom. Now, I'm going to go ahead and place a caveat on this. Number one, you remember when we were talking about the wavelengths of colored lights? And I said, depending on what book you look in or what picture you look at, the numbers sometimes vary from 720 to 780 down to 320 and 380. But 400 or 700 was a reasonable range, right? Same thing with electronegativity. Why we can't agree to a scale, I don't know. The gentleman's name who created this was Linus Pauling, and we're going to talk about him at a later date. But I'm going to use a simple trend. I'm going to show you those numbers in just a second. But I do want you to write this down and note. The value, the electronegative value of fluorine, and don't ask me why this is the values he assigned, is 4.0. Why is it not 5? Why is it not 10? Why is it not 100? I don't know. Fluorine's electronegative value is 4.0. Okay? No, just 4.0. It's electronegative value. Now, to show you a comparison, francium's electronegative value is 0.7. So, you now see the value of the biggest bully? You now see the value of the biggest nerd. there's pretty big range there, right, in comparison of the two. Okay? I know that that's not a huge range, but in this world it is. Yes, ma'am? 0.7. 0.7. Okay? So why I told you all of this, and I want to show you is, we can actually use the numbers on a periodic table to actually calculate and determine the bond type. Now, I've already said this. Are you going to have to do this for this class? No, and the reason why is this big blue sentence in the middle. And I want to address it first. Electronegativity differences are not strictly defined and varied. So if you can go to 5 different textbooks, and they may be slightly different in every book. Again, I don't know why. I'm not the scientist on that. I just have to deal with what the replications are. So this is why we're not going to do it mathematically, because it could totally be wrong. They're in general the same, but there are some slight variations. So here's what I want to do. What you can do is you can take any two atoms. You can take their electronegativity value and subtract them from each other. And then, once you get the answer, you take it and you connect it to a bond type. Let me give you an example. Who's the biggest bully? Fluorine. So I'm going to take fluorine. I know this is really, really, really small. Can anybody see that number on the periodic table? It's 4.0. Remember, didn't I take it was 4.0? All right. Now, let's take lithium. So we're going to let lithium and fluorine bond. Can anyone see what lithium's number is? 1.0. Now, you should be able to do this math. What is 4 minus 1? 3.0. So here's my question. Inside this green box, there are 3 different ranges. Is 3.0 0 to 0.4? Is it 0.5 to 1.9? Is it 2 or greater? So if it's 2 or greater, what bond type is it? Let's check it based on what we talked about the very first thing before we began. What side of the periodic table is lithium on, or what side of the stair-step line is lithium on? Left. So it's a metal, correct? What side is francium on? Right. So we have a metal and a non-metal. What type of bond is that? Is that exactly what we got here? Let's do one more example. Let's take chlorine. Chlorine's value is 3.0. Everybody okay with that? What's chlorine always bonded with in your world? Sodium. So let's do this. Sodium's value, and again, I'm getting it from right here. I'm plugging it in. 0.9. Off the table, right here. You can't see it, it's too small. What is 3.0 minus 0.9? 2.1. So according to our range difference, is it 0 to 0.4? Is it 0.5 to 1.9? Is it 2 or greater? Is it ionic? Yes. Let's confirm that. What side of the stair-step line is sodium on? The left. What side is chlorine on?
Right.
Is that ionic?
Yes.
Let's do one more. Let's take nitrogen and oxygen. Oxygen is 3.5. Nitrogen is 3.0. And again, I got those right off the table. What is 3.5 minus 3? 0.5. So my question to you is it 0 to 0.4? Is it 0.5 to 1.9? Yes. So what bond type is it? Polar covalent. I'm going to talk about polar and nonpolar in just a second, but let's confirm that it's covalent. What side of the periodic tables of the stair-step line are both of those elements? So is that covalent? Yes. Are we okay with that? Let's add one new step of depth. Because I know what you may be thinking. Well, what makes nonpolar and what makes polar? I'm going to give you 2 words. If it's nonpolar, write this word. It is equal. If it's polar, it's unequal. Those are the 2 most important words in this particular section. Okay? All right? Now, this is what we've already talked about, but I'm putting it in words. In ionic bonding, the differences in electronegativities between atoms causes the less electronegative element. So here's what I want you to do. The one that's less electronegative in an ionic bond is typically the metal. So if it's the metal, what side of the stair-step line is it on? Left. If you want to write that in, that's cool. So it's left of the SS. So now let's reread that one more time and keep going. In ionic bonding, the differences in electronegativities between atoms causes the less electronegative element to do what with its electrons? Highlight that. Make sure you know that. In an ionic bond, what happens to its electrons? It is completely given up. I cannot stress that importance enough. In an ionic bond, electrons are completely given up. The result forms an electrical attraction between cations. What's the sign of a cation? Positive. And an anion. What's the sign of an anion? Negative. Now, I'm going to add some depth to yesterday. That little small first bullet may not mean a lot, but here's what it means. The number of positives and negative charges must what? In a chemical formula, how is that achieved? The subscripts. The subscripts balance the charge. So remember yesterday when I kept asking you, do the numbers matter, do the numbers matter? Not at all in determining the bond type. The subscripts matter making it neutral. So out beside this word right here, where it says must equal, please write the word neutral. N-E-U-T-R-A-L. Again, one more time. Out beside where it says must equal, write the word neutral. So what's the purpose of the subscripts? To make it neutral. It makes the positives equal to the negatives. So let me show you an example. If sodium is positive, what do I have to make it neutral? Is that thing neutral? Yes. If chlorine, actually check. If calcium is too positive, and I want to try to pair it with chlorine, can I just use one chlorine? Because is it neutral yet? Can I add another one? So if I had to write a chemical formula for this thing, what should I write? CaCl2. Does that make sense? That is how it neutralizes itself. Is every time you have some, you have to do the opposite. Let me show you one more. What if I have potassium? It's 1+. What if I try to pair it with oxygen? Oxygen's a 2 negative. Is that thing neutral? What is it currently? So how can I make it positive? Or how can I make it neutral? Add a potassium. So what would the chemical formula for that thing be? K2O. Now does it make sense where the subscripts come from? So the subscripts are only used to make it neutral. Not anything to do with the bond type. We okay with this idea? All right. So, what two types of things make up an ionic bond? Metals and nonmetals, or what? Ions. How do you know an ion is an ionic bonding? It's in the name. Ions are ionic. That should make sense. All right, let me see what's next. I'm going to stop here because this is going to take a few minutes, and I want to start.